Hello everyone, welcome to Deep Tips. So, how are you? I am feeling a bit cold today. It's after a long time in Bangalore, like weather is chilly. So, I have changed my theme as you can see, a little snowman. Of course, it's not snowing here, but yeah, it's cold this time. So, how are you all doing? I hope you all are doing great. I expect that many students join today so that we can learn together. And if you want to call your friends, please call them so that it's a community learning, right? So I'm waiting for everyone to join, and in few minutes we will start our class. As you can see, topic is written properties of circles. Children, do you remember when did you learn about circles for the first time? If I look back, I think maybe in your kindergarten, right? When your like nursery teacher showed you a shape or different shapes and asked you to identify which of the following is circle, and see where you are today, learning the properties, right? So this whole universe, this earth is round, right? So circles are all around us. It's an amazing shape, amazing, I must say. There are so many possibilities with circles, and today we are going to explore that by doing few theorems, by learning about circles in an interesting way. I'll try to take you away from the rote learning. Okay, children? So, before I start, we will first try to understand the parts of the circle, the important parts of the circle. No matter you have learned it in your previous grades, but it's always good to recall. Recalling the concepts and trying to connect with what we have learned is very important and is always helpful, because when we are able to connect with what we have learned, then we are in a better shape to build our foundation, right? Okay, so you can see on my screen I have drawn a circle, and let's mark the center of the circle, O. Okay, so this is the center of the circle. Now if I draw a line from center to the circumference, a line segment you should say, yeah, let's say this is OP. So this is called radius of the circle, right? So OP is my radius. And what is the diameter? I'm sure you all know about it. If we double the radius, we get the diameter. So this RS is the diameter. Do you remember? Are you able to connect something else with the diameter? Like I told you in the beginning, that try to connect with your previous knowledge. So if you have learnt about chord, we can say diameter is the longest chord of the circle, right? So chord is the line segment which connects two points on the circle. So this RS is the diameter as well as chord. But if you want me to draw another chord, we can say this AB is also a chord of the circle. Now, when I talk about chord, another thing comes to my mind. That is segment, right? Then now area bounded by a chord and the arc of the circle gives me segment. I'll change the color to make you clear. Now, if you look here, this AB is the minor arc, smaller arc, okay? And this is my this AB. If I cover this entire part from here to here, yeah, so this is the major segment. Okay, this is my major segment, and this is minor segment. So this is something very important. Okay, segment we use in different ways, so we learn about it, but for now it's important to understand what is a segment. Segment is the area bound by a chord and the arc of the circle. Okay, now if I extend this chord, if I extend this chord to both the sides, what it is called? Then it is called a secant. Secant intersects a circle at two distinct points. So it is intersecting at point A and B. So this is called a secant. But if I draw another line here which is just touching the circle at only one unique point, that is called a tangent. Or you can say, if I bring this secant here, then what will happen? If I bring it here, let me draw it little neatly. 1 minute. Yeah. So if I bring my secant here so that A and B coincides, then it becomes a special type of secant which is called a tangent. Okay. So tangent is a line segment which touches the circle at a unique point. So this is the difference between secant and tangent. That secant intersects at 2 points and tangent touches at 1 point. Okay, children. So there is one more thing that you need to know is sector. You know about pizza slice? You all like to eat pizza slice, right? So when you eat a pizza, you take out a triangular part kind of thing from the entire circular pizza. So that is your sector, which is bounded by two radii. So here if you look here, OP and OM are the two radii, and this is my pizza slice. So this is called sector. This is my sector. Okay. So these are the different parts of the circle. So we discussed about radius, diameter, chord, tangent, secant, then segment, sector, right? So this was just a basic introduction of the parts of the circle. I hope many of your friends have joined with me. So let's begin theorem of the day. Okay, so my first theorem, okay, so first theorem says angle in the semicircle is right angle. Okay, now this is the simplest theorem. Angle in the semicircle is right angle. So just now when we were learning about different parts of the circle, we learned about diameter also. Okay, so diameter divides the circle in two equal parts. So here I have drawn a circle with center O and diameter PQ. So children, wherever you draw an angle in the semicircle, it is always a right angle. So let's see how this is possible. Okay, so when we prove something in geometry, we always do constructions. So I am also constructing one radius here. Okay, so this OR is my radius. Now can you again connect with something? Yeah, some kind of triangle. Can you visualize? Yeah, this, yes, I can clearly see this OR is equals to OP, right? Because they both are the radii. OR is equals to OP. So this is which kind of triangle? Triangle OPR is an isosceles triangle, right? So we know the rule of isosceles triangle, that equal sides have equal angles opposite to them. So I can say this angle is equals to this angle. So angle OPR is equals to angle ORP, right? So all these things we have learned in our previous grades, where we have learned about different types of triangles, right? Angles and the different properties based on them. So if I say, okay, this is x and this is also x, okay children, and I have divided, you can clearly see that this angle PRQ, just a minute, this angle PRQ, I have divided this angle with this radii OR. So can I mark it Y here? Angle ORQ. So angle PRQ is equals to x plus y, right? So I can clearly say here, children, this OR is equals to OQ. Yes, OR is equals to OQ because they both are also radii. Yeah. So this is also Y angle. I hope till here everyone is clear that my PRQ, that angle in the semicircle that I have to prove is right angle, I assumed it as x plus y. Okay, so then I used isosceles triangle property. OR equals to OP, so angle ORP equals to angle OPR, both are equals to x. And here OQ equals to OR, so I can say ORQ equals to OQR is y, right? But how do we reach here that this is 90 degree? How do we reach here? This is the question, right? Now I want you to think of one more property of triangles, one more property that is based on exterior angle property of triangle. So what does exterior angle property of triangle says? That if you extend one side of the triangle and the angle formed on that side is equals to sum of two opposite interior angles, right? So this becomes your 2x, correct? And this becomes your 2y. Am I right? Yeah, because if I take triangle POR and I extend the side OP, I get this exterior angle ROQ, which is equals to sum of opposite interior angles. So two interior angles are x. So x plus x gives me 2x. Okay. So now I can clearly say angle POQ is 180 degree because it lies on the straight line. So straight line angle is 180, we know that. So 2x plus 2y is equals to 180 degree, right? And if I take 2 common, my x plus y is equals to 90 degree. So which is my angle PRQ. So hence I can say angle in the semicircle is right angle. Okay, so if you draw one angle here or if you draw another angle here, all the angles are going to be right angle. So angle in the semicircle is a right angle. Okay, so my second theorem is very important theorem, okay, which says angle subtended by an arc, angle subtended by an arc at the center of the circle is double the angle on the remaining part, on the remaining circumference. You must be knowing this theorem. Yes. So this is a very important theorem that is asked in board exams. Okay children, angle subtended by an arc at the center of the circle is double the angle on the remaining circumference. Try to read it carefully. Okay, so my circle looks quite beautiful now. Yeah. So this theorem says if this is your center, okay, this is my center O. Let me draw it first for you. Okay. So can you see here I have my arc AB. Okay, this arc AB. So this arc AB is subtending this angle at the center O, okay, and this angle on the circumference. So let's mark it P. So this arc AB is subtending angle AOB at the center and angle APB on the circumference. Now the question says the angle subtended at the center is double than the angle on the circumference. So let's try to understand how do we reach here, that how is this possible. Okay, so I told you that we need to do few constructions while proving things in the geometry. So let's construct one line here. Okay, so if you see I have done a partition here. My line is passing from the point P to O. So this OP is my radius which I have extended. Okay, so if I divide this angle APB in two parts, I can write X and Y, right? I can write angle APB is X plus Y. So my APO is X and BPO is Y. Now children, can you identify some triangles here? Some sort of special triangles that we used in the previous theorem also. Yes? So here I can see isosceles triangle again. You can see OP equals to OA. Yes, OP is equals to OA because both are radii. So angle OPA is equals to OAP. Both are X. Correct? Same way, you can see OP equals to OB in triangle OPB, right? So when I'm saying triangle OPB, OP equals to OB, right? So this is also Y using isosceles triangle. Now again, see, again I'm using the same kind of properties which I used in my previous theorem. Angle in the semicircle is right angle, right? So here if you see, I have extended this line OP. So we can use exterior angle property. So here it is 2x and this will be 2y, right? Because in triangle APO, if I extend side OP, it is equals to, let's mark this point as D. So angle AOD will be equal to sum of opposite interior angles. So which are x plus x 2x for AOD, and for BOD they are y plus y 2y, right? So my angle AOB is equals to 2x plus 2y, which is double of x plus y. And what is my x plus y? My x plus y is angle APB. So I can say my angle at the center is twice the angle on the circumference. So this is how we prove this theorem in the simplest way. That's why it is said that angle at the center is double the angle on the circumference. Okay, but you must be thinking, okay, here it is direct when angle is just on the top of the angle which is at the center, right? You must be thinking, okay, that in this diagram here I have angle at the center and here I have angle just on the top of it. So I am dividing it and I am doing it. There is one more way to prove it. Okay children, so let's understand it other way also. Suppose my diagram is bit different from what I have drawn. Okay, so let's say this is my angle in the center, fine, and here is my angle on the circumference. Now it looks bit complex than the previous diagram. So if this is my A, O and B, and let's mark this as C. Now what we have to prove? That angle at the center, that is angle AOB, it is double than angle on the circumference. And what is the angle on the circumference? That is angle ACB, right? This angle ACB. Fine. So how do we do this? In the previous question we drew a line and divided, and we used some properties of triangles. So here also I'll do a bit of construction. So let's join this. Oh, just a minute. Let's join this OC and name all our angles. So if you look here, this OCB angle can be seen in my diagram. Can you identify the radii? Yes, there are 3 radii: OC, OB, OA. Correct? Can you identify some triangles which are isosceles? I can clearly see 2 isosceles triangles in my diagram. Can you name them? Yeah, anybody? Can you name which are the 2 isosceles triangles in my diagram? Yes, I have triangle OAC. As you can see, OA and OC are equal. Correct? So if I mark this Y, this is also Y. Right? These two are Y. So I can say, okay, in triangle OAC, OA equals to OC. So I have angle OAC equals to OCA Y. Right. Now I need to mark something, this angle BCA also. Let's say this is angle X. Okay. So now when I'm saying this angle is X, and I told you there is another isosceles triangle. Which triangle is that? Triangle OCB, right? So I can clearly see this complete angle OCB is X plus Y. So here also I have OC equals to OB, correct? So angle OCB will be equals to angle OBC, which is equals to X plus Y. Okay, so I have done all the easy part so far. Now as you can see that I have marked angle ACB as X, and I want to reach at angle AOB, the center angle, and it should be 2 times X. This is what I need to prove. Yeah, so can you tell me? Yes, Vanch, that's correct. Just now I saw your messages. The triangles you have mentioned in the comments are absolutely correct. So very good. Now children, we have understood the isosceles triangles, right, and the angles marked in that. Now the thinking part is, how do we reach angle AOB? How do we reach angle AOB? That, and we should be able to prove that it is twice the angle ACB. Okay, so I'm giving you some thinking time. If anybody know how to do it, you can mention it in the chat. Okay, so no problem. If you can see here children in my diagram, I'll use green color now. Okay, can you see one angle here? Again, for the third time I am using exterior angle property. If you look here, for the third time I am using exterior angle property. Now let's mark this point as D. So if I look at my triangle DBC. Okay, and I extend the side BD. Okay, I shall extend the side BD. So angle ODC will be equal to sum of the opposite interior angles. So that is equals to x plus y, because this angle is x and this is x plus y, which is equals to 2x plus y. Right, children? So we know that for triangle OAD, for triangle, this triangle OAD, exterior angle is same. If I extend the side AD, my exterior angle is same. This is angle ODC, which is equals to 2x plus y. Just now I have written it, correct? So if you look at the opposite angles, sum of the opposite angles for angle ODC, which is equals to y plus angle AOD or AOB, correct? And we know that ODC is 2x plus y and one of the angle is y, so AOB is, to make the equation equal, AOB will be 2x. That's how we reach here. So see, again, what did I use? I just used isosceles triangles, right? Then exterior angle property, and then I equated the equations to reach at my center angle. So these are the two ways to prove that angle subtended by an arc at the center of the circle is double the angle subtended by it at the circumference of the circle. Okay, so this is how we do this theorem. This is a very important theorem, and in ICSE exam many a times question comes from this theorem. So that's why understanding it is very very important, so that you know how it is proved and how it is done. Okay, so our third theorem is angles in the same segment are equal. Okay, angles in the same segment are equal. So I'll quickly do it because this is the simplest theorem. Okay, we'll just try to understand by looking at the diagram. So children, when we proved the previous theorem where I said, okay, angle subtended at the center is double than angle subtended on the circumference. Oh, just a minute, my diagram is not looking so great. I need to redraw it so that you understand it better. Yeah. Pardon me for my drawing skills. Yeah. Okay, let's draw it again. So yeah, this is my one angle and this is my another angle, and this is another angle. Okay children, so I think it looks better than before. Yeah, so let's mark the points A, B, C and D. Okay, so what is written in the theorem? Angles in the same segment are equal. I told you what is a segment. Segment is the area marked by a chord and the arc. So if I look here, this is my arc AB. So this arc here, if I join this AB, I get a segment also, correct? But angles in the same segment are equal, or angles subtended by the same arc are equal. Okay, so if you look here, these angles are subtended in the major arc, in this major arc, correct? So how we prove it? Because we just did in the previous theorem that angle at the center is double. So if I mark this as 2 theta, I know angle on the circumference is theta, and this will be theta. So now these two angles are equal because they are in the same segment and they are subtended by the same arc, correct? So this way, it doesn't matter how many angles you draw in this segment, they all will subtend the same angle. Okay, they all will measure same. So angle ACB, angle AEB, angle ADB, they all are of same measure, and angle AOB is double of those angles. So that's why angle in the same segments are equal. So I hope you are clear with this theorem. This theorem is mainly used to calculate the unknown angles. Okay, so this theorem sometimes come for 3 marks question where they give you few angles and you have to find the unknown angles. So what you do, then you use this theorem to calculate the unknown angles in the given question. Okay. Okay, so now you have understood about the major arc and minor arc, right? So now we are going to do something very interesting using that properties that we have learned so far. So you will be amazed to see that how we collaborate them and find a new theorem out of those. Okay. Yes, so once you have a question here, if O is 20, then the other angles will be half. So what I'm understanding that if you are saying that if center angle is 20, then the angles on the circumference will be half. Yes, then angles on the circumference will be 10 degree. Correct. And if angle at the center, like subtended by an arc, is 40 degree, then all the angles subtended by the same arc on the remaining circumference will be 20. So half of it. At the center, angles are always angle subtended at the center is always double than the angles on the circumference. I hope you are clear. Okay. So now let's do something very important and interesting. Okay, so now children, first I am drawing the figure, then I'll explain you. Okay, so I need 3 circles to explain you. Okay, okay, so I have drawn 3 circles. Now pay attention. Okay, you will be really like surprised to see how we derive a different kind of theorem from what we have learned so far. So don't blink your eyes, just look at my screen very carefully. Fine. So first of all children, you have learnt about minor arc and major arc. Okay, so if I just highlight a small minor arc here which is AB. Okay, this minor arc is subtending one angle at the center and one on the circumference. Okay, so this is O, this is let's say C. Okay children, so if this is here theta, fine, so this will be 2 theta. So what you were saying once, that if AOB is 20, ACB will be 10. So I have just assumed here ACB as theta and AOB 2 theta. This we have already learnt in the second theorem, right? Now children, this was the minor arc AB. Okay, this was minor arc which was subtending one angle at the center and one on the circumference. Now suppose you have a major arc. So here is my major arc that I am highlighting now with green color. Okay, so this is my major arc. Now think how it will subtend angle and where it will subtend. Of course, it has to subtend at the center. So let's subtend. Now the question is, if I just mark my center, just a minute, yeah, here is my center O. If I mark the angle the same way, like how I did 2 theta in my minor arc, then there will be no difference, right? And this is my major arc. So here I will take a reflex angle. So this is the angle that is subtended by major arc at the center. Okay, major arc will subtend a bigger angle, a reflex angle at the center. And where it will subtend the angle on the circumference? So let's draw that. So this is the angle that it is subtending at the circumference. So let's mark it as alpha, and this is my 2 alpha. Okay, I hope this is clear to everyone. Major arc and minor arc, how they are subtending the angles at the center and on the circumference. Now comes the interesting, very interesting part. Okay children, now I'm going to collaborate these two, because I know a circle is composed of minor arc and major arc. So let's blend them together. So what will happen, let's see. So when I was taking my minor arc, I was drawing something like this. Okay, and for my major arc I use this part. So for minor, this is my 2 theta. Okay, and this is my theta. And when I constructed my major arc, I took this 2 alpha and I took this alpha. Now let's mark the points A, B, C, D. I am naming it something like this. Okay, so let me make it little neater. So what can you see here children? What kind of diagram is inside the circle? Can you see 4 points on the circle? A, B, C, D? Yes. So this is a cyclic quadrilateral that we have learnt already, yeah, right? So this is a cyclic quadrilateral. Now in the center, can you see, if I add this reflex angle 2 alpha plus 2 theta, what is the sum of these two angles? The angles around the point, how much they measure? Yes, you can type your answers in the chat. So how much these angles measure? When I ask you, okay, what is the value of the angle around the point? So what is the answer? It's 360 degree. Correct? So alpha plus theta is 360 by 2, which is 180 degree. So what do I get here? Alpha plus theta is 180 degree, right? So I do have a property that opposite angles of a cyclic quadrilateral are supplementary, and hence it is proved. So here theta and alpha are the opposite angles of a cyclic quadrilateral, right? And their sum is 180 degree. So hence I can say sum of the opposite angles of a cyclic quadrilateral is supplementary. Okay, okay, there is one more way to do this, like how we did that theorem previously in two different ways. This theorem can also be proved in other ways. So here I just joined minor arc and major arc and I completed this quadrilateral. But suppose you are given a different type of quadrilateral here, okay, a regular one which looks something like this. Okay, so this was my fourth and this was my fifth theorem, no, fourth theorem, right? Yeah. So now I am proving this with another method. Here I have my regular quadrilateral. Okay, so yes, once this theorem is there in ICSE syllabus, proof is not there in ICSE this year children. In reduced syllabus there are no proofs from circles in ICSE, but for CBSE students proofs are there. There are three theorems, 2 to 3 theorems are there from tangents and intersecting chords. When I come to that, I'll let you know. But proofs for ICSE, completely there are no proofs. For CBSE, there are proofs for 2 theorems. Okay. So let's focus on how to prove this uh, theorem? Opposite angles of a cyclic quadrilateral are supplementary when we have a regular kind of quadrilateral or normal figure that we normally do. Okay, so to prove this, let's construct diagonals. Okay, so these are my diagonals, and let's mark it A, B, C and D. Now children, if I ask you, just look at the diagram and tell me, if I am marking this angle Y, which angle is Y? Which angle is equal to this Y angle? Can you tell me by looking at the figure? And which theorem you will use to say that? That angle BAD is equals to angle, which angle? Angle BAD is equals to which angle? Can you tell me? It is equal to angle BCD, because just now we have learnt that angles in the same segment are equal. Okay, angles in the same segment are equal. Okay, now let's try to find out more angles which are in the same segment and label them. Okay, so now if I mark this part as X, CAD, so which angle is equals to angle CAD? Using angle in the same segment are equal. Yes, angle CBD. This is also X. Now let's mark this angle. This is my Z, angle ABC. Now if I look at angle ABC, angle ADC is also angle Z, because they are also in the same segment. Now one angle is left, which is BDA, so let's take it W. BDA is W, so then ACB is also W. So see, these all angles I have marked based on which property? Angles in the same segment are equal. Now we know that angle sum property of quadrilateral. Yeah, so when I say angle sum property of quadrilateral, that means angle A plus B plus C plus D is equals to 360 degree. Correct? So angle A is X plus Y, angle B is Z plus X, angle C is W plus Y, and angle D is C plus W. So these all are equals to 360 degree. Okay, so now 2x plus 2y plus 2z plus 2w equals to 360, and if I take 2 common, I get x plus y plus z plus w equals to 360 by 2. Correct? So now if you see here, I can group them together. So x plus y plus z plus w equals to 180 degree. Correct? So here x plus y is angle A and z plus w is angle D. So see, I have proved that sum of the opposite angles in a cyclic quadrilateral is supplementary. Okay, so opposite angles of a cyclic quadrilateral are supplementary. This is very important. In many questions it is used. So this is how we prove. And if we rearrange this thing, if we write x plus z and then y plus w, then also we can write angle B plus angle C is equals to 180 degrees. See, both the opposite pairs are supplementary. Now I want to do a little extension in this theorem, which is also a part of ICSE syllabus. Okay, if I extend this side CD, and I mark a point E here, okay, so I can draw one angle here, BDE, and children, as we can see that angle BDC plus angle BDE will be equals to 180 degree. Correct? And we know that this plus this is 180. So if I'm saying that this angle and this angle is equals to 180, that means this angle BDE, it should be equal to angle A, correct? So that means that exterior angle of cyclic quadrilateral is equal to the opposite interior angle. So this is another theorem which says exterior angle of a cyclic quadrilateral is equal to opposite interior angle. Okay, so I hope you are clear with this extension. Please look at the diagram again. Now, just to make you more clear, I'll explain you this once again. If I extend this side, suppose, okay, I can mark one angle here. So then these two angles will be angle on the straight line. So their sum is equals to 180. But we already know that this angle and this angle, they are supplementary. So if these two angle, okay, if these two angles are supplementary and these two are also supplementary, then this angle DBE is equals to angle ACD. Okay. Yeah. So this is the extension property, very important. Exterior angle of a cyclic quadrilateral is equal to opposite interior angle. I hope you all are clear with this. Okay, so children, we are done with the basic properties of circles. Now we will continue with tangents. Okay, properties of tangents in a circle. So there are 3 to 4 important theorems that you need to know, and CBSE board students, grade 10 CBSE board students have their proofs also. So please pay attention. In ICSE, they have specially mentioned that this year, due to pandemic condition, they have reduced the syllabus to numerical application questions only. So proofs won't be coming. But in CBSE, you have proof of 2 theorems. Okay. So one theorem that in CBSE is tangent and radius are perpendicular to each other, and the other theorem in CBSE is that two tangents drawn from an external point to a circle are equal in length. So CBSE students should pay attention to the proofs, and ICSE students should also understand how the proofs are done. It's very important. And in my next video, I will be doing the practice questions based on all these theorems. So I will be doing an extensive practice session with you all tomorrow on the questions, numerical questions based on these theorems. So in my today's video, we are going to cover total 10 theorems, which entirely covers the properties of circles. So if you know those 10 theorems, I'm sure you will not miss any question asked in the board exam. Okay, so please pay attention and stay tuned. So this is my next, yeah, 1 minute. This is theorem number 7 now, which says tangent and radius are perpendicular to each other. Yeah, tangent and radius are perpendicular to each other. So children, the conventional proof you will find in textbook. I am not going to do that for this theorem, because for me it's important that you understand the logic behind it. So we are going to do this theorem using secant properties. Okay, so now again I'll be needing 3 circles here. Yeah. Okay, so my circles look quite beautiful. I'm happy. Yeah, so Let's draw a secant here and mark it as A, B, and the points where it cuts the circle are M and N. Now this is my center O. Okay, so if I join these, I get MON at the center. I hope this is clear, children. I drew a circle and I marked the center O. Okay, then I drew a secant AB which cuts the circle at 2 points M and N. Okay, so now if you look here again, which triangle you identify? Isosceles triangle, because OM and ON are the radii. So my angle OMN is equals to angle ONM, because these two sides are equal, right? And this is my radii. So now let's mark this center angle as X and these two angles are equal, so let's mark them as theta. Okay children, so if I take the angle sum property of my triangle MON, I can write X plus theta equals to 180 degree, correct? And this is X plus 2 theta equals to 180. So my 2 theta equals to 180 minus X, so theta is 90 minus X by 2. So I got the value for my thetas. Both my thetas are 90 minus X by 2. Okay, now if I want this angle AMO. Now I know that angle AMO plus angle OMN, this is equals to 180 degree. This AMO plus theta is 180 degree because it's on a straight line, right? So my AMO will be equals to 180 minus 90 minus X by 2. I am writing it directly. So my angle AMO is equals to 90 plus X by 2. Correct? So this angle is 90 plus X by 2 and this angle is also 90 plus X by 2 because they are equal. Okay? I hope you are clear with the first part. Yes, hello Parth. How are you? I hope you are understanding everything. Yeah? So great to see you. Okay. So children, I hope you are clear with the first part. Okay. Now what we are going to do now, I am going to shift this secant little down. Okay. Then you observe what is the difference. I am bringing my secant here now. Rest everything remains the same. And here is my center. And this is my angle X. This is theta. Everything else remains the same. So what do you think? Does the value of my angles changes? Like in terms of variables? This will remain same. Everything here, like how I calculated earlier, it will remain same. 90 plus X by 2, right? And inner part is 90 minus X by 2. But tell me, how do we figure the difference? What is the difference here? Can you see some kind of difference in the diagrams when I shifted the secant down? See, in my first diagram, secant was somewhat closer to the center, right? But in my second diagram, I brought my secant quite down to the like boundary arc of the circle. So what happened at this point? So this question goes to Ashwin, who has joined today. So, okay, can you tell me, Ashwin, when my secant is closer to the center, at that point my MON is X, and when I brought my secant down, at that point my angle becomes greater or smaller? Yeah. So children, as you can look in the diagram, my angle becomes acute. In the first diagram, angle X was obtuse, right? In the second diagram, angle became acute, right? So this way it's, you can clearly see that this angle is decreasing. Now when my point M and N coincide. Just a minute, I'll draw a better. I mentioned somewhat in the beginning that secant is a special type of tangent, because a tangent is a, yes, correct Ashwin, it got smaller. So tangent is a special type of secant, because here both the points of my secant are meeting or coinciding at one point. So you can clearly see that both my m and n joins here. Okay, so what happened to angle x? Yeah, just think. I hope you are clear with the concept that why tangent and radius are perpendicular to each other. Yes, children? So here x, see, in the first diagram x was obtuse. Okay? In the second diagram x was acute. But in the third diagram, as we brought secant down and down and down, and then it became a tangent eventually when it touches the circle, at that point my x is 0, approximately 0. Correct? So that's why here it is forming a right angle. Okay? So that this is the reason that why tangent and radius, they are perpendicular to each other. It all starts with the secant, and when secant starts sliding down and down and down, and it becomes 90 degree when it touches the circle at one point, then you get right angle. So this is the main reason behind this theorem. So I hope you are clear. We are just left with two more important theorems. Okay, so I'll be back. Okay, children. Hey, Jia, so good to see you. Yeah, I can see your chat. Welcome to Deep Tips. Okay, children. So, this is theorem number 8, which says, and this theorem is very important for CBSE students from the proof perspective. Okay, because in CBSE they have clearly mentioned that proof of these theorems may be asked in the paper. But in ICSE, as I am stressing again and again, due to COVID situation, this year they have specifically like removed the proofs. Okay, so children, but it's important for everyone to learn the proofs, to know that how it is derived, because that's the interesting part of theorems, that how you can twist the geometry and how you can explore it more, and how you derive many concepts from a one single shape, right? So now this is important theorem, that two tangents okay, I'll write it down. Two tangents drawn to a circle from an exterior point are equal in length. Okay, two tangents drawn to a circle from an exterior point are equal in length. So let's try to understand that how it is derived. So here is my circle, and I have to draw two tangents. And this is my common point P, and here is the center. So this theorem says that whenever you draw two tangents which starts from a common point, okay, so then their length is equal. So here my tangents are PA and PB, and basically we have to prove that PA is equals to PB. And to prove certain things we need few constructions. So let's draw the radius of this circle. So OA and OB is my radius. Okay. So children, like just now we did one theorem which says that tangent and radius, they are perpendicular to each other. So can we use it here to prove? Okay. So now, but before I start the proof, let's do one more construction. I want to join this point P to point O. Okay. So now OA and OB are my radius that I have constructed. I have joined O to P. Okay. And here we have 90-degree angle that we have just learnt that tangent and radius are perpendicular to each other. Okay, fine. So now let's think that how we can prove that. Like in your middle school you have learned when two triangles are congruent their sides are equal. Can you identify two triangles here? Yeah, okay. So two triangles here are triangle APO and triangle BPO. These are the two triangles here. Now, how can we prove that they are congruent? We can clearly see two angles, right angles here. Yes, I have right angles. Angle PAO equals to angle PBO, each 90-degree. So I got one condition here. Then my radii are also equal. OA equals to OB. So I got some side, okay. You remember one of the like concurrency rule which says RHS rule. So I have R here, I have S here. Any idea about hypotenuse? Yes, we know that side opposite to 90-degree is always the longest side, and that is hypotenuse, right? So OP equals to OP is common side, and which is your hypotenuse. So I can say triangle APO is congruent to triangle BPO using RHS congruency rule. Clear? So then we can say okay, PA is equals to PB using CPCT rule. Corresponding parts of congruent triangle. CPCT is corresponding parts of congruent triangles. Okay, then you know what, there is one important information that when we prove two triangles congruent there are three pairs which are proved using CPCT. Okay, so one is these two angles, because here sides were already given, one pair of sides we have proved. So that means these tangents are equally inclined to the line joining the point to the center of the circle. Okay, that's why angle APO is equals to angle BPO. Okay, so that means these two tangents are equally inclined. So both are equal, APO and BPO. Okay, this is also because of CPCT. And then these two tangents, they subtend equal angle at the center. So that means this angle is equals to this. So angle AOP is equals to angle BOP. This is also CPCT. Okay children, AOP is equals to BOP. So see, from one theorem which says two tangents drawn to a circle from an exterior point are equal in length, we actually prove three things. One thing, PA is equals to PB, that is the length of the tangents are equal. Okay, second thing, that these two tangents subtend equal angle at the point which is connected to the center, that is angle APO equals to angle BPO. And the third point is that these two tangents subtend equal angle at the center, that is angle AOP equals to angle BOP. So this is something very important. Sometimes in tricky questions where they ask you to find the angles, you can use these results, angles results, where you can, where suppose if angle AOP is given, and then you can directly use this theorem and write BOP is equals to AOP, and then you can proceed with the sum. Okay, so this is theorem number 8. Okay children, so now this is our ninth theorem, which is a very general result. Okay, that if two circles they touch each other, okay, externally or internally. Now see, if two circles they touch each other, suppose externally, I'll draw internally also. My this circle is going little out, so let's darken this one. Fine. Okay, so if two circles they touch each other externally or internally, the point of contact and the centers. Okay, so this is the center of my circle. A and B are the center of my circle, and this is the point of contact for both of them. Let's say this is point P. They all are collinear. So A, P and B, they all lie on the same line. So same goes with this internal circle also. This is center A, this is center B, and here P is the point of contact. If I draw a line here, tangent here, okay, so they all three lie on the same line. So if you ask me, ma'am, how do we do this? So I think I don't need to answer you, because you can directly use the thing here, the tangent and radius are perpendicular to each other. So you can see here that AP is the radius. So this AP, this is angle 1, this is 90 degree, and this is my angle 2, this is also 90 degree. So if I add angle 1 and 2, you get a straight line, and that's why APB, they all falls on the straight line and they are collinear. I hope you are clear with this theorem. This is a very simpler one. Okay, and the last theorem of this session, that is theorem number 10, and this is the very important for ICSE students especially. And children, from this theorem 4 marks question generally comes in the exam, which is very scoring if you know the theorem well. Okay, so I expect everyone to pay attention on the screen that what I am writing and explaining here. So this is the last theorem and the very important one. I hope you all get it properly and score well in exam. Okay, so now this theorem says the angle between a tangent and a chord. So first I'll draw a circle. Okay, so I need one tangent. So this is my tangent PQ. Okay, this is my tangent PQ. Okay, and I have a chord now. Here I have a chord AB. So this theorem says the angle between a tangent and a chord through the point of contact. So here I have a tangent PQ, okay, and I have a chord AB. Fine. So they both are having a contact point, point A, correct? So if you have angle at this point of contact, like suppose you have angle BAQ, so that BAQ falls in the minor segment, correct children? As I have explained you many a times that when I am taking a smaller arc, like here if I take this arc AB, so this arc with this chord AB forms a minor arc. So suppose if I have one angle here, this angle BAQ, then angle formed in the alternate segment will be equal to this angle. Okay, so then this angle will be equal. Okay, so BAQ should be equal to angle ACB. Okay, just a minute. Yeah. So this is the first point in this theorem, that angle between a tangent and a chord through the point of contact is equal to the angle in the alternate segment. Now see, for angle in the minor segment, alternate angle will be in the major segment, correct? So if my BAQ is in minor segment, pay attention here that BAQ is in the minor segment. So alternate segment is the remaining major segment, the bigger part. So angle ACB in the major segment, which is subtended by the same arc, same chord, okay, on the same chord, it will be equal to BAQ, correct? Now Suppose I have angle in the major segment, that is this angle. I am marking it double. Now on this chord AB I have drawn the angle in the major segment, this PAB angle. Okay, so then the angle it is equal to will be in the minor segment, right, at this point. So this will be equal to angle ADB. So PAB will be equal to angle ADB. So now the important thing is, how do we do this? Okay, now children, how do we do this? This is the last theorem and very important one. So basically we have to prove that angle BAQ is equals to angle ACB, first part. Okay, BAQ equals to angle ACB, and second is angle PAB equals to angle ADB. This is the main result of this theorem, and in short this theorem is also called alternate segment, angles in alternate segment theorem. So this is the short form of this theorem that you write in exam. So whenever in exam you solve the questions, okay, so rather than writing the entire statement in brackets, you can write angles in alternate segment. If suppose two angles are equal because of this theorem, then you should write angles in alternate segment. Okay, so now let's do it quickly. So to prove this I need some constructions. So here I have center. Suppose I have my center here. So first I need to draw a diameter. Okay, and then I'll just complete this here. So this is my R and here is my center O. Okay children, so let's mark some angles. First of all, if you just look here, that in triangle ABR. Now in triangle ABR, what is the value of angle B? The first theorem that we did today in our live stream, that angle in the semicircle is right angle. So my angle ABR is equals to 90 degree, correct? Let me mark these angles as alpha and this much angle as beta, so that it's easier for me to write quickly. So now if I'm taking triangle ABR and one of my angle is 90 degree, this angle is 90 degree, then sum of the remaining two angles will be 90 degree. Alpha plus beta is also 90 degree then, right, using angle sum property. Now if I mark this angle as gamma, okay, so this is beta, this much. Okay, I'll highlight it with green. So this is beta and this is gamma. Okay, so beta plus gamma is also 90 degree, children, because we know that radius and tangent are perpendicular to each other, correct? So if we look at the first and second equation, I can, sorry, not, this is not the first one, just a minute. Yeah, this is my first one and this is my second one. Okay, so from 1 and 2 I can say alpha plus beta is equals to beta plus gamma. Yes, so here beta got cancelled, so my alpha is equals to gamma. So my alpha is angle ARB and gamma is angle A, not A, sorry, BAQ, correct? BAQ. Now I have to prove that BAQ is equals to ACB, correct? BAQ is equals to ACB, but I have proved that it is equals to ARB. Now can you see that this ARB and this angle, they both are in the same segment, correct? So this is also alpha, right? So BAQ equals to ACB. So indirectly they all are equal to alpha. So I assumed gamma in the beginning just to make you understand the sum of different angles. So now if I just take away all those variables and I come to the nomenclature of the normal angles here, I can just write alpha equals to gamma here. So angle BAQ is equals to angle ACB, because here my angle BRA is equals to BCA, that is because of angles in the same segment. So my first pair of angles is proved. Yes, my first pair is proved, BAQ equals to ACB, right? So now how do we do angle PAB? Okay, PAB equals to ADB. Now if you look here, this is my PAB, okay, and here is my ADB. I have to prove these two angles are equal. So this is very easy to do. First, children, can I say here that angle P, okay, these angles PAB plus BAQ is equals to 180 degree, because they lie on the straight line. So PAB plus BAQ equals to 180 degree. And if I take a cyclic quadrilateral here, okay, if I take cyclic quadrilateral ACBD, so here my angle C is equals to angle C plus angle ADB is 180 degree. We have just done in one of the theorem that in a cyclic quadrilateral, if you can look at my diagram, I know space is little over occupied here, so I shall erase the previous work so that you can look at the diagram and understand. Okay, so here if you look here, all these angles add up to 180 degree, PAB plus BAQ, okay, straight line. And then if I take the cyclic quadrilateral ACBD, okay, then angle C plus angle ADB is 180 degree. So I can write here angle C plus ADB 180. Now I can equate these 3 and 4. So from 3 and 4, angle PAB plus BAQ is equals to angle C plus angle ADB. But how do we do this? Now here I can clearly see that this PAB plus BAQ, this BAQ and angle C are equal, because we have just proved here, so they get cancelled, BAQ and ACB, from this result. So then angle PAB is equals to angle ADB, hence proved, right? So this is how alternate segment theorem works. So here basically what you have to remember, that if one angle is in minor segment, then other will be in major segment, because that is alternate to minor, right? Minor to major and major to minor. So tomorrow, children, we will be doing many more practice questions based on these theorems, these 10 theorems. So I'll be bringing the best questions from board exams tomorrow for all of you to practice and get well prepared for the exams. So I hope you are clear with the concept. Okay, children. So I hope you enjoyed the session and got a thorough idea of the properties of circles, right? Thank you for tuning in, and please call your friends next time to practice together, so that we all can learn together and grow. Thank you so much for watching Deep Tips. So